Hello everyone, this is Puya. In this video, I'm going to talk about merge sort and quick sort. These are two divide and conquer algorithms based on recursion. So we'll discuss merge sort first, and then we'll see how quick sort can be done using recursion. Okay, so first of all, before we start talking about merge sort, let's talk about another problem. Let's assume that we have two sorted arrays or vectors. So L1 is a sorted array, L2 is a sorted array, and we want to merge L1 and L2 into a larger array with N1 plus N2 elements that's also sorted. Okay, so this is the problem that we want to solve first. So you might think that, oh, let's just like combine these two together, cascade L1 and L2 and sort it, right? But this is going to be very inefficient because we are not taking advantage of the fact that L1 and L2 are separately sorted. So one solution for merging two sorted algorithms would be like this, that we have, like, let's say array X and array Y that are sorted. Each one is sorted, and what we can do, we can allocate a new array with size n1 plus n2, and then what we're gonna have three different variables, each one as an index for each of these arrays that we have. So let's say like I, j, k, or like we can call these variables anything we want, right? So what we're gonna do, we're gonna compare xi and yj. Whichever is the smaller, we're gonna put in the result k, right? So here we compare 1 and 3. 1 is a smaller, so 1 goes here. And then we increment the corresponding index. So in this case it was j, and of course we're going to increment k at each step. Now we're going to compare xi and yj again, right? I is still 0 but j is 1, so we're going to compare x0 and y1. This one is smaller, so this goes here. We incremented I. K is going to be incremented at every step. Compare 5 and 10. 5 goes here. Incremented j. 10 and 25. 10 goes here. 23 and 25. 23 goes here. 25 and 54. 25 goes here. Finally 54 and 75, right? And at this point we have moved all the elements of x into the result array, right? So in that case, whatever is left in y, it's going to be bigger than all the result elements up to this point. So now we're going to transfer all the remaining elements of y into the result array. Okay, so that's how we can merge two sorted arrays. The big O notation of this algorithm would be big O notation n. We only had a loop that goes from index k equal to 0 all the way to k equal to n minus 1. So like at each point we filled one element of this array. Either it came from x or from y. Okay, so this is basically how the merging can work. So this is a C++ program that would merge two sorted character arrays. Let's assume that these are C strings, so we're gonna merge these two C strings into a larger sorted C string. So let's say, like, assuming C1 is ACEG, which is sorted, and C2 is BDFH, which is sorted, right? We want to merge them into a larger array which is also sorted. Let's call it C, right? So what happens here, now you can see that we have three variables, index, which we're going to use it for the result array, I, which we're going to use for C1, and J for C2. Okay, and then this loop goes from index equal to 0 to index less than size of the result array. Okay, so length 1 plus length 2 in this case. Okay, and at each step we're going to increment index, of course, right? And then inside this loop, what we have, we check as long as there are elements inside both arrays, let's say in this case C1 and C2, that haven't been moved to the result array. So what we're going to do, we're going to compare array 1I and array 2j. Whichever is the smaller is going to go to the array index. This is the result array. Okay, and if array 1i is smaller than array 2j, then array index is going to become array 1i, and then we're going to increment I. So this is post increment. It means that array index is equal to array 1i and then I plus plus. And if array 2j is smaller than array 1i, then array index is going to become array 2j, and then we increment j. Once we move all the elements of one of these arrays, either this condition becomes false or this condition becomes false. So as a result, the whole thing becomes false, right? So we check which array still has elements that hasn't been moved to the array, the result array. So if I is still less than length 1, we know that we still have some elements in the first array that hasn't been moved to the result array. So we're going to move everything now from this point on from array 1 into array. And if j is less than length 2, it means that the second array has elements that haven't been moved to the result array. So we're going to move everything from array 2 into the array. Okay, so this is the loop that we have. It's big O notation n. Because this was a C string, we added a null character at the end. Okay, so this is how we can merge two sorted arrays into a larger array which is sorted. And you can see that we only have one loop, which is going to be of big O notation n. Now let's look at another problem. Let's have just one array, right, which it's divided into two sub-arrays. The first one goes from start index to the midpoint. The second one goes from mid plus 1 up to the end index. And each of these sub-arrays are separately sorted. So first array is from start index to the midpoint. This is sorted. This is the precondition. And the second sub-array, which goes from mid plus 1 to end index, is also sorted. Okay, now we want to write a function that merges these two sub-arrays so that A, which is the array, is like becoming sorted, right? So the goal is to make A sorted, right? We have two sorted sub-arrays. We want to merge them so that we have a sorted array. Okay, so first of all, we find the size of the array. So we allocate a new array with the same size. I initialize all the elements to 0. I find the midpoint at this point. Okay, and then we're gonna have, similar to the previous example, we're gonna have three different variables. One is I for the first subarray, one is j for the second subarray, one for k for this new array that we allocated. Okay, and what we're gonna do, it's gonna be very similar to the previous example. The previous example was a for loop. Now we have a while loop. It doesn't matter. You can use either a for loop or a while loop. Okay, so what we do, again, as long as I is smaller than equal mid, it means that as long as we have elements inside the subarray that hasn't been moved to the temp, and there are elements inside the second subarray that hasn't been moved to the temp. We compare AI and AJ. So we compare elements of the first subarray and the second subarray. Whichever is the smaller, we're gonna move it to the temp, right? And we're gonna increment the corresponding variable. If the element of the first subarray is smaller, we're gonna increment I. If the element of the second subarray is smaller, we're gonna increment J. Okay, and eventually we're gonna get to a point that we move all the elements of one of these subarrays to the temp, right? So this condition becomes false, right? We check which subarray still has elements in it, right? If I is still less than equal mid, it means that we still have some elements inside the first subarray that hasn't been moved to the temp, right? So we're gonna transfer all the elements of the first subarray into temp. Otherwise, if j is smaller than end index, it means that the second subarray has elements that hasn't been moved to the temp, right? So we're gonna move elements of the second subarray into the temp, and of course we have to increment either I or j. Okay, and at each step, of course, we're gonna increment k, which is the index we use for the temp array. At the end of this loop, we have a temporary array with the same size as A that is sorted. We haven't touched A itself. So A is still the same as the original array that we had, right? So what we can do at this point, we basically transfer all the elements of temp back to A, okay? So the precondition for this function was we have an array that is comprised of two subarrays, which these two subarrays are sorted. Now we want to merge these two subarrays so that the whole array becomes sorted. This function would take care of that. Once we transfer all the elements of temp into A, we can deallocate temp because we don't need it anymore. Okay, so we used an extra memory space here, like of the same size as A, right, to make this temporary array sorted, and then moved all the elements of temp back to A. Okay, so this is the backbone of merge sort. In order to understand merge sort, you have to understand this function very truly. Another version of this can be written like this, so that the midpoint is given as one of the parameters. So like we know that the first subarray, which goes from start to mid, is sorted, and the second subarray from mid plus 1 to end is sorted, and this is how we can write it. Okay, again, this is big O notation, and don't get confused with three loops here, because these are not nested loops, right? So like here, like we are transferring all the elements as long as there are elements in both subarrays that haven't been moved to the temporary array. And here, like we move all the elements, like in these, like one of these two loops, we're going to enter one of these two loops, and we're going to copy the remaining elements either from the first subarray or from the second subarray into the temp. So this is the same thing. Okay, one point that I should mention here, in this example or the previous example or this example, there is no condition on the size of these two arrays to be equal. Okay, they don't have to be of the same size. This one can be smaller than this one, or this one can be larger than this one. The same thing here. There is no condition for these two subarrays to have the exact same size. Okay, here, because we are dividing it by 2, like finding the mid by average of a start and end index, if the size of array is even, then these two subarrays would have the same size. But if the size is odd, the first subarray would have one extra element, which doesn't matter. Like we didn't use the, like we didn't assume that the size of these two subarrays have to be the same. Okay, so like keep that in mind, that the size of these two subarrays are not necessarily the same. Okay, the same thing here. So what is merge sort? Merge sort, it's a divide and conquer algorithm that says that if you want to sort an array of size n, let's divide it into two subarrays. Let's sort the first subarray first, and then sort the second subarray, and then merge them together, combine them together. Okay, so we are dividing the n elements of the array into two subarrays of n over 2 elements. Again, like I mentioned, that if n is odd, then one of these subarrays would have like one extra element compared to the other one. Then we sort these two subarrays subsequently recursively using merge sort, and then we combine them. Let's look at how this is gonna work out. Okay, so we have an array of size 8 here. So we say in order to sort this one, we're gonna divide it into two subarrays. Okay, we want to sort this one first and then sort this one. Okay, so now we have to sort this one. I don't know how to sort it. So what do? Again, we divide it into two subarrays. Okay, so now we're gonna sort this one, then sort this one, then merge them together. Okay, so now we have to sort this one. So again, I don't know how to sort it. So I'm gonna divide it into two subarrays, sort this one first, sort this one second, and then merge them. Okay, if you have one element, it's already sorted. This is also sorted, so now we can merge them. So merge them into, like using the function that we just saw, we can merge them into a sorted array. So this subarray is now sorted. Now we have to sort this one. So we don't know how to do it. We're gonna divide it into two subarrays. This is already sorted. This is already sorted. So now we can merge them. Okay, so we sorted this subarray, we sorted this subarray. Now we can merge them together. So this is sorted, this is sorted. We can merge these two together. Again, comparing the corresponding elements. 14, 23, 14 goes here, 23 and 45, 23 goes here, 45 and 98, 45, and then eventually 98 goes here. So we wanted to sort this one, it's already sorted. Now we have to sort this one, the second subarray. Okay, we're gonna apply exactly the same approach. So divide it into two, sort this one. I don't know how to do it, so divide it into two subarrays, merge them. Now we have to sort this one, divide it into two. This is sorted, merge them. Now this is sorted, now we have to merge them. 6 and 33, 6 goes here, 33 and 67, 33 goes here, 42 and 67, 42 goes here, and 67 comes here. So now this is sorted, this one is also sorted. Now what do we have to do? We just have to merge these two sorted subarrays. Compare 6 and 14, 6 goes here, 14 and 33, 14, 23 goes here, 33, 45, 42, 45, 67, and this remaining element goes here. So this is how merge sort works. You divide the array into subarrays. Okay, sort the first subarray, sort the second subarray. But we are not actually doing any sorting. We are dividing all the way until we get one element in the subarray. right? When you have one element, that's the base case, right? This is already sorted. Okay, so that's how the merge sort works. So merge sort is comprised of two functions. The first function was the merge function that we already saw. The merge function assumes that we have an array that has two sorted subarrays, and we're gonna merge them together. Okay, so the second function is the sorting function, which takes the array in a start index and end index. Okay, we find the midpoint, right? We're gonna call the same function recursively. We're gonna call the same function recursively, right? But this time sorts the same array from start index to mid index. Sort the second subarray from mid index, sort this array from mid index plus 1 to end index. Once these two are sorted, we're gonna merge them together, right? But this is gonna go forever if we don't have a base case. What's the base case? The base case is we only have one element in the array. So as soon as the start index comes equal to end index, that's it, we return, right? Because an array of size 1 is already sorted. Okay, so this is basically how merge sort works. It's comprised of two functions. The merge function that we saw earlier. Let me go back here. The merge function that we saw here, or this version, doesn't matter which one you use. Okay, and the sorting function that is here. This one is recursive. The first one wasn't recursive. This one is recursive. Okay, uh, the big O notation of merge sort is big O notation n log n in base 2. Like most of the time we don't mention base because for big O notation we don't care about coefficients and bases. So this is big O notation n log n, and it's proven that for sorting we can't have a big O notation smaller than this. Okay, so this is the smallest that we can get for an array of size n. Okay, how this is going to be proven, I'm not going to prove this mathematically, but I'm going to show you like tentatively like how this can be derived, like how this is like big O n log n. So if you think about the merging part is big O notation n. We saw that already. And the dividing part, right? So we are dividing an array of size n into two halves. These are either exactly the same size or one of them has one extra element, right? We are dividing it by 2 until we have only an array of size 1. Okay, so how many of these steps do we have? We have log n base 2 of these steps, because basically if you think of this is 1 multiplied by 2 multiplied by 2 multiplied by 2. 2 multiplied by what number is going to become 2 times what 2 raised to power x is going to become n. So x has to be log n in base 2. So for the division part, we have log n in base 2, and at each of these steps we have to do merging, which is going to be of big O notation n. So the total running time of merge sort is big O n log n. One small disadvantage of merge sort is that merge sort is not in place. If you remember when we did the merging part, right, we had a temporary array, so we had to have an extra memory of size n, or big O of n, right, and we had to move all the elements from A into this temp first and then move them back into A. Okay, so it's not an in place merge sorting algorithm. It needs extra space, and these copying, it takes a little bit of time. Okay, so one of the advantages of merge sort is that, like, whenever we divide the array into two sub arrays, the two sub arrays are almost equal size. If n is even, they're gonna be exactly the same size. If n is odd, one of them is a slightly bigger, but like they almost have the same size. The depth of the recursion, it's going to be big O of log n. The amount of the work done at each level, like for merging, it's going to be big O n. So intuitively, the complexity should be of big O n times log n. There's an O missing here. The amount of extra memory used is big O n. This is the temporary array that we used for the merging part. Okay. So that's all about merge sort. I have a practice question for you that I want you to do merge sort for a linked list. So let's see if you can apply merge sort for a linked list. This is gonna be a very interesting problem to solve. I'm not gonna do it for you. I'm gonna ask you to solve this problem. So this is like a um, like a like applying the same algorithm for a linked list instead of an array. Okay, now we're gonna talk about quicksort. Okay, quicksort is another divide and conquer algorithm. It's very similar to merge sort in the sense that we divide the array and we try to like basically like work on a smaller sub array instead of sorting the original array. Now, before talking about quicksort, let's talk about another problem. So this problem is called partitioning. Okay, let's say that we have an array, okay, that we wanna, like, that it goes from index low to index high. Okay, and in this case, I'm choosing the last element of this array. You see that array high, it's the last element. I'm choosing this as a pivot. So here we are basically saying that this is going to be pivot. What does that mean? It means that now we want to partition this array so that this pivot, by the end of this function, it would be moved to the correct location that it would have in a sorted array. Okay, it would move to the correct location that it would have in a sorted array, and all the elements inside the array that's smaller than the pivot should be on the left side of this pivot, and all the elements that are larger than the pivot should be on the right side of the array. Okay, so this is basically this partitioning problem. Based on your C++ knowledge so far, you should be able to write this program. It's written for you here, but you should be able to do it yourself. What we do here, we basically have two indices, two variables. One is basically to count how many numbers are gonna be smaller than and then the pivot, right? So we go through all the elements of the array from low to high, and we check if they are, sorry, all the way to high minus 1, because we chose high as the pivot. Okay, so we check all these elements to see if they're smaller than the pivot. If we find something smaller than the pivot, we're gonna swap it with the element at the beginning of the array. Okay, and then we're gonna increment this I index, okay, that we use for swapping, right? And then we check the other elements. If we find something is smaller than the pivot, we're going to move it to the beginning of the array. We're going to move it to the beginning of array. Of course, like I is going to be increased at every time we find a smaller number than pivot, right? So this is like how partitioning works. At the end of this function, like, oh, okay, sorry. Once we are done with the loop, we haven't moved the pivot yet. Now we know how many elements are smaller than pivot. So now we can like swap the pivot with the correct element so that pivot is going to be moved at the right location. By the end of this function, we have an array that one of its elements, in this case, which was the original last element, it would be moved to the correct location, right? And all the elements smaller than the pivot, it's going to be on the left subarray. Every element that's larger than the pivot, it's going to be on the right subarray. Okay, so that's the result of this partitioning, right? And we return the index for the pivot, like once we swap it to the right location. Okay, so this is what partitioning is. Keep this in mind, because similar to merging, which was the backbone of merge sort, partitioning would be the backbone of the quick sort. Okay, so like so here, using this pivot, using this partitioning, we basically partition the array into two subarrays. Now, one of the disadvantages of quicksort compared to merge sort is that these two subarrays that are going to be made are not necessarily the same size. One of them might be size 0, the other one might be size, let's say, n minus 2. Or like n minus 1. One of them might be size 1, the other one size n minus 2. They're not necessarily like the same size. It depends on the composition of your array and like what element you choose as the pivot. So here we chose the pivot as the last element of the array, right? But we have freedom on choosing which element should be the pivot. In this example here, in this program here, we have the same function, but we choose the first element as the pivot. Instead of choosing the last element as the pivot, here we choose the first element as the pivot. And again, we do all the swapping so that all the elements smaller than the pivot, it's going to be on the left subarray. Everything larger than the pivot would be on the right subarray. And finally, pivot is going to be moved to the correct location. Okay, so this is basically what partitioning is. Like here, like if we choose this one as the pivot, right, we select the pivot partitioning element, rearrange the list so that all the elements in the positions before the pivot are smaller than or equal the pivot, and those after the pivot are larger than or equal the pivot. Exchange the pivot with the last element in the first sublist. Okay, right? If pivot was the last element, we should exchange it with the first element in the second sublist. And then we're gonna now, like, we divide the array into two subarrays. We're gonna apply the same thing into these two subarrays. Okay, so this shows an example of quick sort. So here we are choosing 15 as the pivot. Okay, so 12 is smaller than 15, 3 is smaller than 15, 21, 25. So basically, by the end of once you, like, if you follow this algorithm, by the end of but like, so like here, like we are like here 21, so here 21 is bigger than 15, because here, like, we're starting with the first index. We check which elements are bigger than 15. This is bigger, so we're gonna move it to the last element. 25, we're gonna move it to the last element. 3, no, 9, no, 8, no, 18. So like here, like all the swappings happens here, like between the elements, and then 15 is gonna be placed in the right place. Like you see, like finally we swapped 15 and 9. Okay, so that's what we did. Like, and if you look at this, all the elements smaller than 15 are on the left side. Okay, all the elements smaller than 15 are on the left side. All the elements larger than 15 are on the right side. Okay, so here you see that like we swapped 21 and 5, and then like we swapped 20. Yeah, so like here, like again, like 25 and 8 were swapped, and then so on. Like, so here, like you can see like all the swappings that happened here, and then eventually 15 and 9 were swapped. Now we have two subarrays. You can see that they don't have the same size. Now we're going to apply the same partitioning for this subarray and this subarray. Okay, so we choose 9 as the pivot, right? We move it to the right location. Everything is smaller than 9 is going to be on the left side. Everything larger than 9 is going to be on the right side. 25 is chosen as the pivot. It's going to be moved here. Everything is smaller. This is like the partitioning. Everything is smaller than 25 is on the left side. Everything larger than 25 on the right side. And then this keeps continuing. We're going to have more sub arrays. We're going to do exactly the same thing here. Choose 8 as the pivot. Here choose 12 as the pivot. Here choose 21 as the pivot, 28 as the pivot. And once we finish this, right, once we get to only one element, everything becomes sorted. This is quick sort. So it's a divide and conquer again. Like, so here, like we pick a random element as the pivot, partition the array into two sub-arrays, right? And then we have recursion. We apply the same method. We call the same function for this array and then this array. Okay, so this is basically similar to merge sort. Quick sort is also made of two functions. The first one was the partitioning part that we saw before, and the second one is the recursive function that's called quick sort or sort, right? So you can see here that here we partition the array, we find the index of the pivot, right, and apply the same method. So like call the same function, this time for array in the low with the same low index all the way to pivot -1, and like call the same function like quicksort function for the same array from pivot +1 all the way to high. Okay, and this is gonna continue, right, until low becomes equal to high, right? Once low becomes equal to high, we have only one element in this in the array, so the array is already sorted. So this is like basically the base case. Okay, or you can say like instead of this we could say like if low is equal high, return, and then this is going to be a separate block outside this. So this is what quick sort is. One thing that I should mention about the quick sort, and like one problem that I mentioned here, is that ideally in a divide and conquer algorithm, we want to divide this array into two same size sub arrays. But depending on the configuration of the array, this might not happen. So you can try that. If you have an array which is reversely sorted, if you choose the pivot as the last element, what you end up with a subarray with size n-1 and another subarray which is 0. So this is basically not working out because we are not reducing the size that much. It's like reducing only by one element. So that's why, depending on the choice of pivot, like in the worst case scenario, you might even get like big O notation n², right? So this is the case that, for example, if you have a reversely sorted array and you choose pivot as the last element or the first element, right? If you do that all the time, you end up with like a sub array with size 0, or like you might end up with a sub, like if you have a different array, you might end up with a sub array of size 1, which is not ideal. We want to divide this array into like ideally two same size sub arrays. Okay, so that's why there are choices for pivot, right? So like the quicksort's performance depends on the choice of the pivot. In some algorithms you choose the first element, in some algorithms you choose the last element. In some algorithms you choose the element randomly. So you write a random function that would choose a random element and you choose that one as the pivot. Okay? In some algorithms, before like doing the partitioning, you find the median number, like you find the number that would be in the middle. If the array is sorted, you find the median of all the numbers in the array and you choose that number as the pivot. Okay, so far I mentioned like 4 different choices for pivot. You can choose the first element, last element, randomly, or you choose the median number as the pivot. What's the advantage of choosing the median number? Because once you choose the median number, your two sub arrays would end up being of the same size, almost the same size. Okay, so this is what quicksort is. Just like I know that you guys are tired of watching this video, so like I'm gonna like show you like a small version of another video. This is merge sort. Two sorted subarray. Or sorry, two like dividing into two. Merge. For this one, divide into two. This is already sorted. Divide into two. Merge. Now these two subarrays should be merged. They go back. Right? Now these two subarrays should be merged. Right? This is the temporary array that we have. Right? And then everything remaining goes here. So this is like what merge sort is. Like in the quick sort, we have something similar. Some talented dancers are showing quick sort. So here we're choosing the pivot as the first element. We're comparing all the elements. We see like if any swapping is needed. If 2 is smaller than 3, it's going to be moved. So this is like the partitioning part that we mentioned. They're doing it like a little bit differently than what we mentioned, but like you see that this one was the pivot. The array is divided, partitioned into two sub-arrays. Everything is smaller than 3 is on the left side, everything bigger than 3 is on the right side. And they're applying the same thing for each sub-array. They're doing the partitioning. Another video I wanted to show you is this one. This shows different algorithms. Sorting algorithms, like here selected sort, bubble sort, sort, insertion sort. These are the 5 that they have already seen. You can see how fast merge sort and selection sort, merge sort and quick sort are. Go a little bit further. So this is another configuration of the array. Here in the merge sort, you can actually see how the array is divided into 2. It's very easily shown. Like in the bubble sort, you can see that like everything is sorted from end to the beginning. fast forward. This is quick sort, merge sort, and bubble sort. You see how slow it is. The selection sort, you see how slow it is. Insertion sort, and so on. I have provided the link for these videos here in the slides. I hope that you can watch them. So I just wanted to mention that merge sort and quick sort, both of them are big O n log n, right? On the average for quick sort, depends on the pivot, of course, right? These are going to be very efficient method. Quick sort is usually used like in most software packages, like for large data sets. If you have huge data sets like merge sort, sometimes it's preferred over quick sort. And selection sort, insertion sort, they're very slow, they're in place, and they can be used for small data sets because it doesn't matter like what the time complexity is not that important for a small data sets. One thing I wanted you to remind you about merge sort is that it's not an in place, like while quick sort is in place. Okay, that's all for this video. Thank you so much.